Yeah, okay. Thanks for joining in such big numbers, and sorry for being a bit late. We had a bit of problem with the presentation to get it on both screens. But anyway, great for you to be here, and we like to be back in London after a few years. We're going to talk about MLOps, machine learning in production. A little bit about myself. My name is Bas Geerdink. I'm from the Netherlands. I work as an independent consultant, and you can find me on Twitter and LinkedIn, etc. So we'll be happy to connect. I also wrote some books and articles about this subject, including a playbook and some, a hands-on workshop book. So of course, those are all very highly recommended if you want to know more about MLOps. Okay, let's start with the basics. Machine learning in production. What is this all about? Probably we have some data scientists here in the room as well, and I think when you come to this kind of conference, you've been in touch with machine learning already. But just to grab a bit of the basics again, machine learning is basically about writing algorithms about historical data, learning from data to make a some kind of a prediction. And people who are in this business, who have this as a specialty, have learned many years, have spent many years in university, on other courses and all kinds of subjects, and of course in their daily job to perfectionize this. So this is a highly regarded subject, and it's really a highly specialized field to work in. With many kinds of algorithms, many kinds of types of machine learning, etc. So what happens if you introduce this to your company? That's okay. This is great. We want to make some kind of prediction for whatever kind of product we have. Maybe we want to predict our customer behavior, for example. Let's hire a machine learning engineer, a data scientist, and a machine learning expert. Well, what he comes up with is usually something like this. They get some data. They work. Maybe in isolation a bit on the data, they produce something. They work with the business people, and at the end they say, "Hey, great! I have something ready. I have something that makes a great prediction for you, and this is it." But what is this? This is a notebook, right? This is Jupyter Notebook, the standard typical tool for a machine learning scientist to work with. And that's great, they've put a lot of effort into this, and it works. But how the hell are we going to get this in production? How are we going to make this part of our landscape, of our existing software architecture? That's a problem that was already recognized a few years ago, and it's actually a famous article of 2015 by some folks at Google. They said, even though machine learning nowadays, data science is a highly regarded subject and it requires a lot of effort, it's only still this little black piece of the puzzle that you see in the center here, and all of those things around it should also be recognized and should also be considered. We have to prepare the data, we have to get the data from somewhere, we have to write monitoring tools, we have to manage the model. Basically the same as any piece of software or data or any asset that you have in your landscape, in your architecture. And that is of course where MLOps comes to the rescue, because this is a relatively new subject. The machine learning world is getting a bit mature, and now we start thinking about this kind of problem. How do we actually productionize our models? Many companies that start doing this, they will Google a bit, they will search a bit, they will talk to their consultants or their vendors, and what they come up with is a tool. And I will also talk about tooling in a bit, but I actually think it's more important first to think about the way of working, about the culture first, because you introduce a new type of specialty within your company if you start working with data science. And you start introducing a new kind of special role in your team. And I would like to go back to one of the previous revolutions that we already had, DevOps. The name is also a bit similar, so it's not a coincidence, of course. DevOps, MLOps. Roughly 10 years ago, we introduced this as a concept to integrate software development and software operations, maintenance, in a better way. We introduced DevOps together with Agile software development to cross the boundaries between these kind of specialties. And with the goal, of course, to make software more agile and better maintained and easier to develop and easier to deploy to our infrastructure. Well, guess what? MLOps basically has the same goals if you look at it from the cultural perspective, from the team perspective, from the organizational perspective. So what you could say is MLOps is basically DevOps plus machine learning. You have developers, software developers as a specialty still. You have engineers on the ops side also as a specialty. They are already working together in the same teams, in the squads that you have. And now let's enter a new specialty, the machine learning engineers and data scientists. And of course, I also had to include this diagram because a Venn diagram is very important in every presentation. That's what I learned in doing many years of conference presentations so far. If you don't have a Venn diagram, you're screwed. Right. With the same goals actually as we had before at DevOps. We want to make a better, smoother software development life cycle, basically. You don't want to have data scientists sitting in a corner of your organization in a cellar or so where there's no daylight and thinking about models and calculating algorithms and then throwing it over the fence to some other team who does not know what to do with it. You want to combine the skills of all these people in one team. And I think that's quite important. The data science is so regular in many of these organizations that to do this on a proper scale, you have to treat this as discipline in multidisciplinary teams. And then you will gain trust. Yeah, you'll frequently update your model, so you'll get better at it. You will get speed because you'll do it in a more regular way. You will monitor it better, so you gain a lot of trust and speed in your company when you're working with machine learning models. Of course, your roles and responsibilities in your teams will change a bit because, data scientists are, a new specialty that you will introduce in your teams. And also, there's also one other role that I would bring to your attention, which is the machine learning engineer. Also, a role that is maybe a bit new to a lot of companies, but I think it's quite important to recognize that you need people that are integrating your models that have been built and trained by the data scientists into the applications that you already have, into your architecture. The machine learning engineer is a role that is dedicated for that. Next to existing roles you probably already have, like a dev engineer, an ops engineer, maybe a data engineer. This might look like a lot in your team, but I do want to stress that these 5 roles, the typical data science team roles that you will find in a multidisciplinary squad, don't of course have to be one single person. You can perfectly set up a 3-person machine learning team that works on predicting some kind of value for your customers, like a supply chain delivery time, or maybe a translation algorithm, whatever it is that you apply, and just do it with like 3 people, where you have one person who fills the role of data engineer plus a machine learning engineer, you have one data scientist, and you have one person who fills the role of dev and ops engineer. The number of roles doesn't equal the number of people necessarily. But if you do recognize these roles in your team, then you at least know a bit what to do and what to expect in these multidisciplinary squads that we would have when working with machine learning models. The work itself, of course, changes a bit, and I wrote down some best practices when it comes to working with machine learning models. First of all, going back to the first slide, notebooks, sure, they're great, but I would not recommend using them in production. I would just recommend them using them as a first step to explore your data, to visualize your data, to basically take the first steps to writing proper software, proper code that you can actually deploy to production. your code in your notebooks can of course be taken out of that and taken into a proper script or a proper software application that actually contains the same code, but then is repeatable and testable and deployable. And also versionized, very important. Every code should be versionized in the CI/CD pipeline. Then what comes out of that process, of that model code that you have written, is basically just an artifact. It's usually one file or maybe a set of files that contain your model. Well, the same goes for that. Where you would treat your code as any other code that you would version and maintain in a regular way, that model that you have, you would treat that as any other artifact in your architecture. You probably also have other artifacts like files. Maybe you have images, you have sound files, you have artifacts there. They will also be versionized. They will have a proper metadata on top of them. They will also be maintained, deployed, etc. in a controlled way. But that's the way you should treat your models. Your models should not be somewhere in a notebook and only accessible by some kind of machine learning specialist. They will just have a regular place in your infrastructure, basically. And then we come to the subject of testing and monitoring. Again, basically not so different from all the other software that you would have in your normal application. If you put something in production, you would of course want to monitor it, you want to measure it, you want to look at the metrics, at the logs, etc. But with machine learning models, that comes a little bit. It goes a little bit further than that, because next to monitoring your your technical metrics, your technical measurements, like how much RAM and CPU are you using? What is your latency? Those are the technical metrics that I usually see in normal applications. You also want to measure the business metrics, as I would call them, because your model in production will produce outputs in the form of predictions. Well, those predictions are uncertain. So what you want to do on a regular basis, especially the business people, they want to check if these predictions are not, going askew, going in a wild direction that are completely, unpredicted, are completely out of the ordinary. Because if that is the case, then something might have happened. There might be data drift. That means that your data in production is actually different from the data that your model used to be trained on. And it can happen. Circumstances can happen. Your customers can behave differently from one week to another, for example, because maybe something happened in the world. Maybe there's another energy crisis or something else that causes your customers to behave in a different way. Let's say you deploy a new model every week. That your new model is different from the previous version, so that it just produces different kind of output. It doesn't have to be bad, because that can be the reason why you actually have deployed a new model, but you do want to know that. So what is the normal kind of predictions that my model gives? Let's say normal is the range of 0.4 to 0.7 with a certain normal distribution. Hey, if my average of my prediction is 0.8, okay, something is happening. Let's dive into it. Let's see what's actually the case. Right. Now let's move on to the architecture a bit, because there is, of course, some best practices and some architecture concerns on how to do this. And again, if you look at also this conference, for example, there's a lot of tooling out there that can do this for you. But I don't want to focus on the tooling too much. I want to focus first on the abstract concepts a bit. So what I try to do is come up with like a high-level kind of picture or reference architecture that you can use in basically any case, in most of the cases where you will apply machine learning in production. And then I think you can fill in the tools yourself later. And this is the picture that I came up with. The first version. This goes further than this. Basically, all machine learning applications that run in production follow this pattern. There's two pipelines, that you could call them, two parts. There's a real-time part and there's a batch part. The batch part of the machine learning environment is the part where you train and deploy your model to a certain model registry. This can be done, every year, every week, every day, or maybe even every minute. In this case, the last case, you probably will call it online learning, or maybe even real-time learning, but it will still probably be a batch process, with the goal of producing a new version of your model and deploy that version in a registry, in a basically a location where it can be picked up to be used in real time. There's of course a connection to the real-time pipeline, because that model needs to be deployed, published, served somewhere where it can be used. Usually that model is wrapped by an application, by a service. In this case, I call it's actually I also mentioned it. It's probably an API that wraps your machine learning model so that it can be used by other services. Important to notice is that this model is probably not directly usable. So there's some data preparation, some pre-processing usually going on, and some post-processing to prepare the data in the way that the model can use it, and also to interpret the scores of the model in a way that your business application can use it. And that's of course the boundaries of the machine learning system itself, because then these scores has to be used by an app that actually runs action. And the app can be a website, it can be an app on a mobile phone, it can be a business process that runs somewhere, but that is the way that your integration with your machine learning model happens. One other component already put in this diagram is the feature store. Feature store is a relatively new concept. But basically you could see it as a database, a regular database that contains the features that have been collected, gathered while your app is running. So you also see an app an arrow while your app is running in real time. It actually could collect data and store them as features by calculating them. Let's give an example. One of the features that I usually want to know is the number of sales that have been made by one customer or a group of customers in the last month or the last week. Well, if I would have to use that as a feature in my real-time app, and I would have to calculate that feature on the spot, then that can take quite some time to calculate, so my model would be too slow in production. So what I want to do is calculate that feature up front, store it in a feature store, make it available for my real-time model to be used when I'm evaluating the model, when I'm making a score for this particular customer. But also my feature store needs to use that data, that feature data, when it's training for a new version. So also my training pipeline needs to access this feature store, because it uses that feature to make a new version of its model when it's training itself. So that's where the concept of feature store is quite important. There's dedicated technology for that as well, but you can also just use a regular database, call it a feature store, and probably it also will serve your purpose if you don't have like very, very high requirements for like latency or so. Let's continue a bit. Yeah. Then, while the app is running, you probably also are collecting actuals. And with actuals, it means that you have some data that you want to compare to your predictions. Let's say you make a prediction for a customer he's going to purchase next. So you actually make a recommendation for a customer what he's interested in. And you show that as a recommendation on the screen for your web shop. Well, that's good that you have to make a recommendation. You'll probably store that prediction somewhere. But of course, you also want to know, did my customer actually click on this recommendation? Did he actually follow up on this? And if that's the case, hey, bingo, we have done a good job. We can use that information again, that actual information, to retrain my model again, so that my model is better in the next iteration. Also, if it doesn't click on that recommendation, so my prediction, my recommendation was not good, you also want to know it. Because then we probably have to predict something else in the next iteration for the model. So getting these data is very important, and you have the feedback loop to retrain your model again. Then, logging, metrics, monitoring. Well, basically, as I mentioned already before, whatever your you want to log it somewhere because you want to evaluate on this. You want to check in real time, or maybe in hindsight, does my model predict the things that are kind of what I expect? You will probably not look at individual values, but at the overall distribution of your prediction data. Is it what I was expecting training and building this model? And finally, all of this tooling that we set up need to be deployed in a controlled way with a CI/CD pipeline. So the code for the model needs to be in a version control. The models themselves, they all have to follow a CI/CD pipeline with a including a build process that deploys your software in a controlled way to your development, test, acceptance, production environments. This arrow here actually basically goes for all the tools and software that you have here running. So this might look like a relatively complex picture, but the great thing is that I think if you understand this, you can probably fill in most of your machine learning applications and plot them on this picture. To give a few examples, Google Cloud, I just picked up the biggest vendors that have selected how they do machine learning basically. Well, Google has this reference architecture for machine learning, and guess what? They also have this separation between batch processing for training the model and real-time processing for evaluating the model and integrating that with your application. Of course, Google recommends to use the Google tools. So everything you see in this picture is built on the Google Cloud, on GCP. They use like Vertex AI, and they use the feature store, and they use the model registry, all tools that you can use in the Google ecosystem. But in essence, it follows the same pattern I showed you before. Same goes for Amazon. They recommend Amazon tooling, but the same kind of pattern is in this. And also Azure, same pattern, batch real-time deployed, and using the similar technologies and patterns that are in production. Now, I do want to know, I do know that people are looking at tooling specifically. I do want to say a few words about that. But I don't going to recommend any one or other tool. I mean, that's not my role. I should go to the vendors themselves, I think, or check, of course, if there's something you can build or deploy yourself in open source. Because there's a lot out there. This is a space that is only maturing just in the last 2 or 3 years or so. So it's constantly evolving. If I would recommend one of the tools now, it would be out of fashion in a half a year time or so again, and there will be new ones that do things even better. So what is more important than selecting one of the tools is checking what fits your company. That's what I would really want to stress, because I've seen so many companies that just go to one of those tools, use it, and then after maybe 1 year find out that it's not really what they were expecting, it's not really what their people like to use. So there's a mismatch between the people in the company themselves, the engineers and the business people that need to use the tools and the tools themselves, and that's really a bit of a shame. And basically it comes down to these discussions. Do you want to buy or build? And with build I also mean now using open source tools, because open source tools are never easy to just plug and play. It's also always difficult to integrate, but you can consciously choose for that, because then you don't have a vendor lock-in. You can also consciously choose for a vendor that offers you all of the tooling available, because that's easy to set up, and you have your system running in maybe a few weeks time or so. But that's a conscious decision that you have to make. Not so different from other tool decisions that you have to make. One other thing that is important now is that you also have to find out for the data science part whether you want to use AutoML or you want to build your custom models in-house. Going back again to one of the first slides, your data scientists who have been trained to use all the fancy Python frameworks and tools and Panda data frames, etc. they are also expensive, and they take a long time to build the models. Probably they will build a model that is highly accurate, but in some cases you can nowadays also buy or use models that are pre-trained, basically. Or you can call an API that already contains a pre-trained model. And that goes pretty far nowadays. There's AutoML models for like translation, for customer sentiment analysis. A lot of text-based algorithms are now in some kind of AutoML space available. Microsoft has them, Google has them, other companies also have them. So that is quite valuable to look into that as well. Of course, at the other end of the spectrum is when you really expect models to be trained on your specific company data. If you really have data that is unique for your company, you cannot buy a model for that makes a good prediction for it. You have to train your models in-house, hire machine learning engineers and data scientists that build and train and deploy your models. But also here, there is a conscious decision to make, and there's also a gray area where you could have this discussion internally in your organization. The model serving is, there's a few options for that. Also, I don't want to go into specific tooling too much because there's many options for that, but it's important to realize that there are several useful ways to serve your model, including kind of a monolithic approach. That's the first one. The top one is deploy your model together, packaged with your application. I would not recommend that per se in the first place because it's a bit of a monolithic approach, so you would have less flexibility. But the second and third options are quite common, to deploy your models as a set of models in a dedicated application, or to API-ify your model, to wrap your model with a thin layer that is just responsible for translating data to the features that your model can use. And basically that means that you have a model, which is that file that I mentioned before. That file is hosted as part of your service, as your API, and API just interacts with specifically that single model alone. That's what it's responsible for. And this fits very well, of course, in a microservice architecture, where you have decoupled software, you have services that call each other, etc. Very good approach. But there's also a dedicated or special case where that might not be good enough, and that is streaming. If you have a streaming application where you actually are running, you are processing big data streams, fast data streams in real time, calling an API across a network might actually be too slow. So what you want to do in that case is package your model within your stream, within your running stream processing application. For example, Flink or Spark structured streaming or Kafka streams. Your model can actually should be as close to the data as possible in that case, because going over a network might already be causing too much latency or too much overhead, and then you will have maybe a latency which is too high. There's also tooling for that. I'm not going into specific of that, but I mentioned here PMML or Onyx are basically intermediate formats, similar to like Joplib and Pickle, but are more used in a streaming context because they can be used for these kind of technologies in a JVM-based context. All right, I mentioned the feature store already. I have a slide about it, but I'm going to skip it. And workflow orchestration is also very important. Basically, what you will see in a normal, in basically any of the machine learning projects that I've seen, and I've seen many in many companies before as well, is that workflows, batches are important for many of the cases. You will have batch processes for training your models, sometimes for scoring your models, for deploying your models, etc. So it's very important to choose a proper tool for that that fulfills your requirements and that can do that in a properly managed way. Some examples here: Kubeflow, Airflow. There's also vendor products again that can do this for you. So important to look into this carefully and to also maintain this tool in a good way. Right, I'm out of time, so yeah, this is my wrap up. I mentioned that the notebook is just usually the beginning of your machine learning product. Don't consider it to be your endpoint, the end stage. If you want to apply machine learning operations, MLOps, look at the tooling, but first look at the culture, the team aspect of it, because that's really important. Put the people together who are working towards the same end goal in a certain multidisciplinary squad, and then follow the architecture patterns that I mentioned, and then select the tools that you want to use for this. There's some further readings in here. I'll leave this slide open. You can have a look at this. Some recommended courses, and also a vendor-neutral website for MLOps. And of course, the resource that I already mentioned, Equal Experts has a playbook, and I co-authored a book by Pact about this subject as well. And with that, I want to thank you for your attention, and hope to see you next year. Thanks.